In this video, we're going to extend our discussion on logistic regression. And in fact, we want to look at multiple logistic regression, which is, again, just like multiple linear regression, except that the dependent variable is binary rather than continuous. And we don't make an assumption of linearity, although we do kind of make it linear by taking the logit. All right, and in doing this, we're going to look at the Chow study. And we found an interesting thing with that, and that it looked like in the spherical lenses that there were two types of populations. And we want to see if we can use baseline characteristics of the eye to discriminate between these two populations. So when we look at these data, these are ortho-K lenses, two ortho-K lenses, spherical and aspheric. The open circles are aspheric lenses and the colored dots are spherical lenses, and we're looking at a baseline axial length and a follow-up 5-year axial length. And this black line is the line of identity, so if the axial length grows, which it does over time, then all the values should be above this line. The fact that there are some below the line suggests that there might have been some measurement error in here, be my guess. I mean, I suppose it's possible that they shrunk, but it's pretty unlikely. Now, when we look at the colored dots, it seems as though, well, obvious now because I've added symbols, but it seems like they're almost two different populations. There is this gap in here. It's like a cluster of dots and a cluster of dots. The dots down here, the spherical lenses down in this area, the round black dots, perform pretty much just like the aspheric lenses. Whereas these guys are all outliers, and they're accompanied by a few aspherical outliers. But they're out here, and it just seems like there's an issue going on here. So our question is, can we predict what the future is? Can we predict the future? So we know the past baseline at five years prior, and then this is the 5-year outcome. Can we use those baseline variables to determine how well the child will do in ortho-K? And so that's our mission, and let's see if we can do that. And we're going to do that using logistic regression. And we need to select, oh, wait, oops, sorry. Before we do that, I wanted to just briefly mention how we separated the two. So we want to separate spherical lenses, but we want to do it in an objective way. The way we want to do it is to use aspherical lenses and correlate baseline with axial follow-up and draw a line. It's not shown here, but it comes kind of right down the middle there. And then we want to define outliers. And we're going to define outliers as 2 standard deviations above this predicted line. So there's a line in here, 2 standard deviations above. If you're outside that, you're an outlier. And the dotted line represents that 2 standard deviation cutoff. So all these guys out here are outliers with respect to the aspheric model. Those inside are not. So that's how we've defined our two groups: outliers, not outliers, poor fit, good fit. So now we can go to our logistic regression. Now we only want to look at spherical lenses, so we're going to go in and data, select cases, if lens type equals 0, because lens type equals 0 is spherical. Lens type equals 1 is aspheric. And we do that, and then come down here and we can see we're crossed off if it's aspheric. We're not crossed off if it's spheric. So let's just jump into it and let's go analyze regression, binary logistic. So we have lens type 2. Now lens type 2, there's 3 categories of lenses: aspheric, spheric good fit, spheric bad fit. But we've already deleted the aspheric. So we're left with lens type 2 and 3. So we're left with the spherical good and poor fit. And then we have our baseline variables. So we have gender, we have age, spherical equivalent, keratometry, eccentricity, horizontal vision iris diameter, pupil size, central corneal thickness. And under options, we're going to look at iteration history, just to kind of give a little example. Actually, we're going to do correlation too. Continue. And we're going to enter everybody, so we're going to look at all these variables at one time. Okay. Now what we get, we see we have 177 patients. Good control is given 0, poor control is a 1, so the higher the coefficient, the worse you're likely to do. We have gender there. We have our iteration history. So this is block 0. This is just finding the baseline values. Nobody's predicted to be any poor control 1. They're just, everybody's a 0. This is the base. This is our denominator in our odds ratio. Now this is our handy little table, variables not in the equation at step 0, because this says this is like individual correlations. Spherical equivalent has no impact on KT, so these are independent. And you can see everybody's significant except for age, and gender is only marginally significant. Now this, okay, so now let's go into method 1. And one of the things that we have here is our iteration history. So least squares, like regular linear regression, uses a formula and there's no steps. You just plug in the formula, you get the answer. In logistic regression, it uses maximum likelihood, and it tries something, and these are the values. It tries something else, and again and again and again until it's happy with the, so basically no change in the values, and so it sticks with that. Here's our pseudo R-squareds. We can see that it's between 0.6, 0.8, pretty good. R-squareds, 60 and 80% of the variance. In the pseudo, and they're not real R-squareds, they're pseudo R-squareds, but they give you an idea that your model's pretty well fit. We have missed 18 in the prediction. We've got 159 correct, so that's pretty good. Now let's see, remember up here in step 1, independently, everybody was significant except for age and maybe gender. Down here, variables that stayed in the equation after we looked at the context of everybody else, we definitely lost gender, we lost age, we kept spherical equivalent, we lost keratometry, we gained eccentricity, we lost HVID, we kept pupil size, and we lost CCT, central corneal thickness. That means that these guys were correlated with the others, and so the multiclinarity just took them out as being significant factors. After you've accounted for spherical equivalence, eccentricity, pupil size, there's nothing left to independently account for any significant variance in the model. This correlation matrix, let's look for example at spherical equivalence. There's really, well, maybe eccentricity is kind of correlated, pupil size is kind of correlated, central corneal thickness a little bit, but if we look at E value, well, I guess those are also kind of all low, but they're, we just see that those small correlations, when summed up over a lot of different things, really have an impact on taking the folks out from contributing independently. All right, that is one way to do multiple regression and multiple logistic regression, and probably the, I don't know if I'd say it's the best way, but if you're trying to predict how kids are going to do in 5 years, you might try another alternative, and that is stepwise logistic regression. So we come here, we have everything's the same, but we're going to do a forward walled thing, which means it's going to go find the best variable and it's going to add that, and then it's going to consider that in the model. Then it looks, given that they're spherical equivalent, what is the next best, and so forth. And next best doesn't actually start with this model. So spherical is the best. E value, no, pupil size is second, E value is third, but really it's just this best one, and then it'll reevaluate. It may stay the same, but it does it one step at a time. So our stepwise is going to pick out spherical equivalence first because it's the best. All right, let's try it. So here we go. And we come down here, and basically everything is the same as it was before. Our classification at step 0 is all the same. These are all the variables that were there. Now, in our method 1, where we're going to start stepping, this just shows the iteration history. This really is the only purpose of this is just to illustrate to you the fact that the computer goes through a bunch of steps to try and find the best model it can. It tries a bunch of parameters. You can see it started at 0.572. Then it tried again. It adjusted them a little bit. Got some real improvement again. A little bit of improvement, no improvement, so it stopped. Our R squareds over step 1. So when you add spherical equivalent, you're at 0.381 versus 513 R squared. You go up to more on the next one and a little bit more on the third one. Classification table, we missed 32, and then we missed 20, and then we missed 17. So adding that last one gave us a little bit, 3 more people that we could correctly classify as good or bad after 5 years. The variables in the equation, step 1 is spherical equivalent. Took that out. Then looked to see what came next, and pupil size popped out next. This happens to correspond to the step 0 table, but it didn't have to. And then we come up with spherical equivalence, E value, and pupil size. So we added eccentricity at the end. Notice they're all significant. And then it kind of stopped. We can see when we had spherical equivalent pupil size, our walled was 31. The spherical was 34. Well, when you added eccentricity, spherical equivalence dropped a little bit. Pupil size dropped a lot, and basically the E value gained it mostly out of pupil size. So we have those 2 variables. Now, what this means is if you use the equation A minus 4.429 plus 2.764 times the pupil diameter times minus 9.643 times eccentricity, 0 to 1, plus 1.823 times the spherical equivalent. You add those up, you're going to get the predicted logit. or the predicted, and then you solve for that probability. The probability equals 1, or equals this exponentiating this model divided by 1 plus this model, gives you the probability that you are going to do poorly after 5 years given just these 3 values. Now, exponentiating each variable by itself tells you the odds ratio for each individual one. Notice these numbers vary. They're a little misleading because the scales are so different. I mean, pupil size is a number on a different scale than spherical equivalent, and this is just 0 to 1. So it's a different scale. All right, correlation matrix only includes the ones in this model. The correlation matrix we did before was much better. Variables not in the equation, you can see that these were all significant after you took out spherical equivalence. You still had a lot of significance. Gender even did a little better. But then when you took out the next one, which was pupil size, it knocked out everybody from significance except for eccentricity, which was added in on the 3rd step, and now no one left behind can contribute significantly. So these are the values, the individual values, after you've taken out all the variance from the other 3 variables. And so that's logistic regression, multiple logistic regression.